Welcome, public inventors.
Hello, today I'm going to talk about VentMon, an open source ventilator monitoring device for the COVID-19 pandemic. VentMon is a project of public invention. So today we're going to talk a little bit about the motivation behind developing VentMon, a brief overview of the device, its hardware functionalities, software functionalities, and then we're going to talk a little bit about the idea of modularity in the VentMon ecosystem and the broader open source community. Finally, if you're interested in learning more or helping out, we'll talk about some additional resources available right now. So, on the right-hand side of the screen, you'll see the VentMon device itself. This is sort of a drawing, but the photo is our current version of the device, 0.2. In a typical setup, the VentMon would be connected in line with the ventilator under test and perhaps a device like a test lung to provide feedback on the other end. It would then be connected to a user computer so that the user can collect all the data being recorded. So first, let's talk a little bit about the motivation behind VentMon and the problems we were hoping to address with this device. As the pandemic progressed, we saw a lot of teams, primarily composed of makers and engineers, working together to create open source ventilators to help sort of bridge the gap between supply and demand and the current supply chain. VentMon aims to address that need. It is in and of itself meant for testing and verification of a ventilator device. Our secondary goal with VentMon is to promote modular reuse within the broader community and also within the VentMon ecosystem. No one team is going to have the perfect solution to the ventilator crisis. So by thinking in more compartmentalized ways and breaking down the overarching idea of a ventilator, we can hopefully have many teams solving small parts of the problem coming together to ultimately deliver a more effective and better tested device. Secondly, we wanted to create a better platform for teams to share information and test results between themselves. In a lockdown situation, it's really hard for people to communicate in person. So it seemed incredibly important that we provide a platform which would allow the same type of communal development to happen in a remote way. Finally, as I mentioned, our goal throughout this process has been to promote the modularity of the components in our device and help demonstrate that these modular ideas can be integrated to ultimately improve reuse and compatibility between design teams in this space. So here's just a quick picture of the VentMon in action. You can see this case here on the left contains the main components of it. Much of the sensors are here in line with this test lung, and then this tubing connects to the output of the ventilator under test. And you can see here we've got somebody actually looking at the data coming from the device, making design decisions accordingly. So just a brief overview of VentMon here. So the heart of what we're doing is collecting the physical data from the inspiratory airway. So we're recording flow, pressure, temperature, humidity, and not in this diagram is fractional oxygen. As I said, those sensors are connected to a processor, which allows us to transmit data to a shared data lake using a common data standard. We're then able to process that data and then gather some clinically significant metrics such as minute volume, PEEP, inspiratory to expiratory ratio, and the rise and fall time of the pressure in the airway. Digging in a little deeper here, we've got a photo of the real VentMon. So on the right, you can see our processing and networking components. Underneath this OLED screen labeled A is an ESP32 feather from Adafruit that sits on top of an Ethernet shield from Particle. So ESP32 provides us with Wi-Fi capability, and the Ethernet shield allows us to use Ethernet, obviously. This means that we can still be able to communicate data in a variety of environments. Wi-Fi or Ethernet may not be available, so it's good to have both. Moving to the right, we just have a simple breakout board with a bunch of quick connectors allowing us to connect sensors to our I2C bus. Moving on to the sensors. On the right-hand side there, near the C label, are two small breakout boards for the BME 680 sensor. These come from Adafruit. One sensor is responsible for measuring the ambient pressure, temperature, and humidity inside the enclosure, and the other one is connected via an oxygen tube to the airway to measure the pressure, humidity, and temperature in the airway. Finally, on the left there, you can see our flow sensor labeled D and our oxygen sensor labeled E. Our flow sensors come from Sensorion and are able to measure about 250 liters per minute in either direction. And then our Teledyne oxygen sensor is pretty typical diving sensor. So, talking first about connectivity within the physical components of the device. All of our sensors are connected using an I2C bus to the processor. This gives us pretty quick data transactions and allows us to connect a lot of sensors at once, making the device more expandable as time progresses. That data is processed a bit and then sent via UDP connection to our host, which is running a data logger, and then our server, VentMon.coslabs.com. Finally, a user is able to access that data using their own internet connection and view it in our public data lake. So as I mentioned, pressure sensing is done using the BME 680 sensor from Bosch. We have two of these sensors, one in charge of collecting ambient data and one in charge of collecting the airway pressure. By subtracting the two, we're able to find the differential pressure, which allows us to calculate when inhalation and exhalation occurs. Currently, VentMon supports a variety of Sensorion flow sensors. These were heavily limited early on in the pandemic, since many manufacturers used them in commercial ventilators. However, that supply chain pressure has been alleviated somewhat, and it's now a more stable resource. However, since this device was so scarce originally, we spent a lot of time working with various teams to help develop open source flow sensors. At the moment, we aren't using any of these, but we look forward to cooperating with some of these teams in the future and integrating their designs into the VentMon. Finally, oxygen sensing, as I mentioned, is done using a typical oxygen sensor you would find in a dive shop. So, as I mentioned, there are a couple basic software components in the VentMon. So, as we just talked about, we have some basic firmware collecting data from all the sensors. Next, we'll talk about the basic software components of VentMon. You can see all the main components of our software connected by the public Invention respiratory data standard we've created to communicate that data. So raw sensor data is collected by the processor and then transformed into this byte level format of the PIRDS data standard. That data is then sent to the data logger, which translates the PIRDS data into a JSON format so that it can be easily manipulated for applications further down the line. That JSON data is then sent to our public data lake at VentMon.coslabs.com, where a user can view it using breathplot running in their browser. So the PIRDS logger is one of the core components of our device, and it's responsible for collecting all of that data from the various VentMon's connected. It's continuously running as a daemon on our server, and its main goal is to translate the byte-level PIRDS data into the JSON format for easier processing down the pipeline. Next in that path is the data lake, as I mentioned. It's public. Anyone can go to ventmon.costlabs.com and see real-time data coming from our devices. All the traces from the various IP addresses connected to the data logger can be viewed there, and you can either see them as raw JSON data or using our visualizer BreathPlot. BreathPlot is another key component of VentMon that provides all the clinically significant metrics you'd expect to see in a ventilator. Rob's going to talk a little bit more about that.
Hi, this is Robert L. Reed, demoing the BreathPlot software, which is used with the VentMon device. The first thing I do is go to our public data lake, ventmon.coslabs.com. which shows the public files which have been generated by all the people using the VentMon or any other source of the streaming data that conforms to the public Invention Respiration data standard that we've created. This one is live for us now. I now take my mask and breathe into it. So you can see I'm creating a live trace based on my breaths, which shows pressure and flow. And on the right is being dynamically created a number of clinically important features. Some of these features turn red when they are alarmed. That is, when the breathing rate or some other feature is either higher or lower than a set value. As we can see, the pressure and flow is going by, and so are various events, including the measure of the relative humidity and the fraction of oxygen and the temperature and so forth. Now let me make a full set of breath traces. And I'll just turn it off so that we can talk about it. This is typical of a ventilator. In fact, the VentMon is made to test a ventilator, although I don't have one. You see a pressure graph and a flow graph. Pressure is measured in centimeters of water, and a variety of clinically important numbers are computed on the right, including tidal volume. Each breath is broken up using a basic thresholding algorithm into these events, which are rendered down here as the and on the event graph, and each breath is furthermore broken down into the volume of the individual breath. This one is a 250 milliliter inhalation with a 262 milliliter exhalation. The work of breathing for this individual breath was 1.4 joules per liter. That's an advanced feature. The work of breathing is averaged over here. That is relatively high because the test lung, which I'm using right now, high resistance and relatively low compliance. It's also the case that the system computes the rise time,
the time to go from 10% to 90% of the signal,
of values set down here for the pressure curve. Often a rise time which is too slow or a fall time which is not fast enough is associated with poor or ventilator performance. By clicking this button, I can make it live again. Since this feature is completely distributed, completely free of charge, and done at our public data lake, a distributed team, which is locked down, possibly because of the COVID-19 pandemic, can observe a geographically distributed operation. That is, engineers in one place can observe the ventilator being tested in another place using the VentMon, which also opens up the possibility of telemedicine in the future. This system can be expressed by this diagram showing how the software works. The VentMon, or any other device that produces PIRDS data in the format that we've publicly defined in a GitHub repo as a standard, is transmitted via UDP packets to a logger. The logger produces PIRDS data file in the public Invention Respiration data standard data file format. That is served by a web server producing a JSON PIRDS string, which is read by the browser via AJAX to render the page that you just saw to be examined by an engineer or possibly a clinician.
Back over to you, Gloria.
Our goal here was to break down a standard ventilator into smaller, more modular components so that an open source maker-based team can focus on individual components and tackle the problems surrounding each of those in a smaller, more efficient way, as opposed to tackling the whole challenge of building a ventilator at once. This also allows teams to collaborate. One team can focus on one aspect of the ventilator while another focuses on a different piece. Then, in tandem, we can ultimately create better tested, more satisfactory devices. In the ideal VentMon ecosystem, the ventilator itself is really composed of three core pieces. The air drive, which is the actual device pumping air through the airway. A controller, sort of the brains behind the operation, that gives input to the air drive and tells it when to turn on and off. And then a sensing module, basically the VentMon. This provides feedback information to the controller so that it can tell how to effectively modulate the air drive. So in our ideal ecosystem, we see that the PIRDS data standard is heavily used in addition to another data standard called PIRDS. PIRDS is the complement of the PIRDS data standard, and it provides control commands to the ventilator device. So you can see in this diagram we have measurement data in the PIRDS format coming out of the VentMon being fed back into the controller, which in turn generates PIRDS control data to control the air drive. At the same high level, the user can have some controls over the controller to modulate the air themselves. This again is implemented using the PIRDS control standard. So a typical control pathway would be the user makes a change at the high level with the GUI in the GUI. That's translated to another block of lower level software, which passes it along to the actual controller, which then passes it along to the air drive. Again, in this way, we're able to focus on the core components of the system and ensure testability in those key elements before moving on to tackle the larger challenge of an entire ventilator.
The VentMon's free of charge to people who request it. We've been generously supported by the Mozilla Open Source Foundation and Protocol Labs in doing this to be able to give them away free of charge. It is an open source system, so of course you can build your own and hopefully contribute improvements back to us. But you're free to build your own, or you can request one from us. You're also free to use our public data lake. The request form is at www.pubvent.org/project/VentMon, or you can contact me, Robert L. Reed, directly at reed.robert, that's read.robert@gmail.com.